Good evening.
Hey, John.
Hey, how's it going?
Not too bad. How was your week going?
It's trudging along. Not too bad. I didn't have to go to Greensboro today, so I'm feeling a little bit more rested.
Nice. Um, I was actually just discussing a problem very briefly with Amanda before you showed up. So we'll start with it. This is one you may be able to share with your son. I don't know exactly how far along he is with his math. I know he's still pretty young, but this is kind of a nice little geometry problem that I saw dropped on Twitter by somebody who enjoys writing some problems. And for anybody who might uh, watch the video of this, you can check out this lady. I don't know her, but she posts some fun little math problems on her Twitter account. And here she's got 3 triangles of equal area. So we need to come up with an angle. Any thoughts?
I want to take some time. Sorry, I just saw a text message. Yeah, I talked to Aubrey about it, and he said he sounded interested, but when he tried to download the Zoom app, he got a notification that his OS was out of date, and he
Oh
says the
no!
computer's like 10 years old, so he can't. Yeah, he's not
Oh
going to
goodness!
get a new one.
By the way, Amanda, I'm kicking this out. You locked her in here with me.
See, part of me wants to start brute forcing it with some law of sines for the area of triangles. But since I'm guessing this is a segue into symmetries, I think there's probably
Well,
a more
so
elegant.
I wasn't even really thinking about this problem when I said we were going to do symmetry today.
Oh, okay.
Yeah, and for anybody who tunes in, I think I am going to put this one up on YouTube maybe if it's fun. But
Yeah.
I said that we were going to cover symmetry today. But you know what? Anywhere you've got equality, I guess you could say you've got, you know, a form of symmetry. Symmetry is a word that we can interpret so broadly, and we probably should to make best use of it. But symmetry will be the topic of some of today's conversations. But only sort of. We're going to start with some symmetry, but we're gonna talk about Catalan numbers.
Oh, nice. Okay. Yeah, it's been a long time since I've seen those.
So here we are with these triangles, and what do we notice, or what do we get out of the equal areas?
Well, the pink triangle is 1/3 of the total.
Mm-hmm.
I don't know, the unknown angle plus the other 2 angles add up to 180.
We do have a straight angle, and we will make use of that. The thing I'd jump at most quickly is same base, same height principle.
Oh, yeah.
Either one we sometimes make use of. Oh, I don't like that size pin.
Oh, so they drew it perfectly, and that really does bisect it down the middle. So 120.
Mm-mm.
Oh.
Okay. But if the yellow and the pink triangle have equal areas, what do we know?
Then we know that the 2 bases are the same, so
Right,
that's the bisector of the third. Yeah, the big pink angle is 120, or the obtuse angle in the pink triangle. Which angle am I trying to solve?
I don't know why you say one. I think it could be a lot of things.
Oh,
We have 2 equal sides in the yellow triangle, but not 3.
okay.
Can you scroll up a little bit so we can see the complete question again?
Yeah,
Thank you.
sure. Yeah, look at that green dot. It's conspicuously an endpoint
Right.
of
The green
3
dot
equal
is
lengths.
the bisector of it by that same base height observation that you made.
It is also the center of a circle.
Oh,
Oh,
so there's a 90-degree angle there.
yeah.
Yeah. Oh, hey, Tanya. Thanks for joining us. I didn't notice you'd popped
I
up.
made it.
Tanya, meet Amanda and John. Amanda's my wife, and John's a high school classmate of mine. And we were just working this as like a snack problem, to get started with. But we've got this problem where we had more information than we needed. We didn't really care that the orange area was equal to these. We just found the right angle, and yeah, that's.
Oh, the question mark is the angle.
Yeah, well,
Oh.
yeah.
Okay, I was looking at the obtuse angle and the pink triangle for some reason, but
Yeah, that one we can't determine. Like,
No.
you can shift this diagram in a whole lot of ways. Like, maybe we can actually. I said that very quickly. I should think about it. I just know that we don't need the orange area to be equal
Mhm.
to the other two. Anyway, here's the problem that I actually prepared for today to discuss, which was one that it's funny. I actually I formulated this problem sitting and waiting for a job interview, and then later found out it was a famous problem. It's one of those things where once you've studied more math, you go, oh, obviously this is a famous problem, because it's just kind of fun, and it's not, it's novel when you think you might be the first person to have thought of it, and then you realize, no, of course this is a problem that a lot of people would think about. So let's say we've got a cat at the origin on the number line. Since I just threw the cat out of my office and she went and sat on Amanda's desk instead. Our cat's name is Nissa. So Nissa is going to start here, and we're going to flip a coin. And when we flip a head, Nissa is going to move 1 unit in the right direction. And when we flip a tail, she's going to move 1 unit in the left, or the negative direction, left direction. So what we want to know is, what is the probability she ever makes it back to the origin once we start flipping the coin? I'll write that down. So it's a random walk problem. And
that is a random walk.
There's Nissa.
It's good to have good diagrams
Amanda.
to understand the problem.
Oops, I just turned my screen off. Did that cut it off for everybody else too?
No,
Or can you else?
we
Oh,
can
that's
still
good.
see.
No.
I can.
Yeah, that's good to know. So as we start exploring this, oops. One of the things we start to realize is that we could think of this problem in terms of something like an infinite series. Like, this particular sequence right here that winds up back at the origin has, is a 1 over 2 to the 8th power, 1 over 256 chance that after 8 flips we have the sequence, and we're back at the origin. And we could find, what these sequences are, and have some sort of an infinite summation. And And if I recall correctly, this is doable, but is very, very difficult. I think I came up with a way to do this like 2 years after I originally solved the problem, but I've completely forgotten. But I'm actually going to come back and talk about what the numerators are. The numerators are something called, or at least related to, there may be an adjustment that has to be made, but they're related to something called Catalan numbers, which are kind of famous in mathematics. But so instead of something like an infinite series, we have to look for something clever to find a nice solution to this. And one of the things we realize is, well, there's symmetry. Nissa could go to the right and eventually come home. She could go to the left and eventually come home. But there is a clear one-to-one correspondence due to symmetry because of the binary nature of flipping. Switch the zeros and the ones to zeros. So yeah, this is helpful. It means the probability she begins by going to the right and coming back is the same as the probability as going left and coming back, and that's intuitive. That's nice. So we can focus on the times when she just goes in the positive direction first. So let's say that our first flip is ahead, and there she is. And now what we need is for her to ever get 1 unit over to the left. Ever. And there are a lot of problems in math where once we identify something like ever, we can chop it up. States, if you've ever worked in any state-based probability problems, thinking in terms of quote unquote ever helps us with a lot of those. But what we can do here is break this up into 2 cases. If we're ever going to go to the left, well, we could go to the left immediately, meaning flip a tail immediately. Or we could flip ahead, at which point she's at 2. And then what do we need to do from there?
2 tails.
Specifically, ever get 2 units to the left. That part's important, this ever. It allows us to do something clever at this moment. How do we ever get 2 units to the left? What has to happen first?
1 unit to the left.
Yeah, we have to ever get 1 unit to the left. If we don't ever get 1 unit to the left, we're not getting 2 units to the left, ever. So we can say the probability that she gets home is equal to the probability we immediately flip a tail, or the probability that we immediately flip ahead times the square of the probability of ever moving 1 unit to the left, which is p squared. Because we just defined the left-hand side as p. Probability of ever getting 1 unit to the left. And now we just have a quadratic. Multiply this by 2 and reorganize. And it's a very simple one with only the solution 1. So the probability she gets home is just 1. Yay, we get our cat back. So first time I worked through this problem, and I spent several days working this problem the first time I ever worked it, I filled up a lot of pieces of paper, a whole lot of pieces of paper. The attempt at working a series, that went on for quite a while before I decided to do something else. But okay, so symmetry was nice here, and this is a nice problem with a nice solution. But what can we do to make this problem more difficult?
Change the rule.
How do we change the rule?
I don't know, maybe she goes 2 to the right for every head.
So one thing I want to point out is if her probability of ever moving 1 unit to the left is 1, that would be the same for ever moving 1 unit to the right or ever moving any number of units in any direction. She has a probability of 1 of winding up at any point, discrete point, since we haven't really defined, well, I guess you could say travel in between. So any point on the number line, she'll be there at some point.
XY.
Given enough time, given enough coin flips. What else could we change?
2 dimensions.
We could, but let's stay in 1 dimension for the moment. The 2-dimensional problem takes a lot longer.
We could give her a deadline for getting back home.
We could what?
We could give her a deadline for getting back home.
Okay. Cut off the, like, say it has to be within n flips.
Yeah.
Okay. And at that point we're going to get approximations, and those approximations I believe are going to be based on Catalan numbers. Maybe we'll come back to that. Here's what I was thinking was just weight the coin. If we weight the coin so that moving to the right or left is no longer probability 1/2, what happens?
Your recursive equation changes coefficients.
Well, maybe.
Right. Well, P would be A plus 1 minus A times P squared.
Well, I was thinking, maybe, yeah, that's true. I was thinking maybe as in maybe we take that approach. I think that was the approach that I took to originally solve the problem, and then I realized, oh, it's far simpler than that. If we've already solved the first problem, it turns out this problem is trivially simple, but we have to step back and see the big picture first. If you went to a carnival and there was a guy there with a carnival game, and he said, I've got a weighted coin, 51% head. And you pay $1 to play, and you win $2 if you win. Are you going to bet on heads or tails?
Well, you said 51% for heads, and
Yeah.
so you're at a penny net expected value.
Yep, penny net, 2 penny net
2,
expected value, right?
Multiply.
So you can just keep playing that game forever, right? Obviously there's some percentage chance that you go bust, right?
Yeah, how big is my wallet? how many dollars
right.
do I go?
But it's only $1, so the number of times that it would take, the probability of you going bust is so infinitesimally tiny, 1 over many orders of magnitude. So you're probably just going to sit and play that game as many times as you're allowed. Well, so long as the edge is enough to pay for your time. So we can assume the carny is going bust, right?
Mm-hmm.
We can assume that the game maker is going bust. Okay. Well, let's assume, without loss of generality, that the probability of flipping a tail is greater than the probability of flipping a head. We can always flip it. It's symmetric. Flip this inequality, I mean, not the coin. But this is, and so let's still imagine, though, that we begin by going 1 unit to the right, because, well, that symmetry, that 1-to-1 correspondence that we had before, it still applies, doesn't it? For every path that begins by going right and coming back, by going in the positive direction and coming back, there's a path that goes in the negative direction and comes back. And the probabilities of those, if we make the probabilities flipping head to tail, probability of flipping a head P, probability of flipping a tail Q, where P plus Q is 1. Each of these paths has the same probability, P to the 4th times Q to the 4th. So for every path that goes positive and comes back, we have a path that goes negative and comes back with equal probability. So the two directions coming back has to be the same. Okay. Well, with probability P, Nissa takes one step to the right. What's the probability that she ever gets back 1 unit to the left? What was it before?
1.
1.
1. And now Q is greater than P.
It's still 1.
It's still 1. Yeah. Yeah. Q being greater than 1/2. You know, the chances of going to the left are at least as high as each individual flip. It has at least, you know, the same probability, and then you're adding sequences that get there even faster. So the probability of going to the right, never coming back, is just P.
This notion of ever is somehow quite confusing.
If you haven't worked many state-based probability problems, it probably feels that way. I'll do one more that is a simpler version. That is a simple example of a state-based probability problem, and it will probably make it easier to think of this problem that way. But the probability of going one step to the right and then ever getting back is P, and that must be the same as the probability of starting out going to the left and then coming back. So they must both be P. So 2P is the answer to this problem. Or you could say, if you don't, if you take away the condition that Q is greater than P, you can say 2 times the minimum of
P and Q.
probability of flipping ahead and probability of flipping tail. Yeah, P and Q. So if you weight the coin 2/3, 1/3, probability of making it back is 2/3. If you weight it 9/10, 1/10, your probability of making it back is 1/5. So since this idea of ever is it's a difficult one, you know, when you're first getting accustomed to it. Here's an example of a game that helped me get accustomed to it. Let's say that Tanya and John play a coin flipping game. And this one is going to be asymmetric. Wait a minute, that's 1S, I think. And let's say that Tanya goes first. Maybe she won a coin flip. Tanya goes first. And the winner of the game is simply whoever flips the first head. You flip a coin, you flip a tail, you pass it, and then the other person flips. So the probability that Tanya wins her first flip is 1/2. Probability that she doesn't win, then John wins, is 1/2 times 1/2. The probability that Tanya doesn't win, then John doesn't win, then Tanya wins is tail, tail, head, 1/2 times 1/2 times 1/2. So we wind up with 2 infinite geometric series. And you know, we could compute these. We could also do some algebra, and we could say, hey, the probability of Tanya winning plus the probability of John winning is 1. But hey, look, it's clear that Tanya's probability of winning is twice John's probability of winning. So we could do this with infinite series. We could do this with algebra, and applying algebra to probability problems is something that's not natural to us at first, but it happens a fair bit. But here's the state-based solution. There are 4 states in a game, and we'll use a simple graph to show the connectivity of those states. And those states are named Tanya's turn, John's turn, Tanya won, and John won. If we get to Tanya won or John won, the game ends. Otherwise, it moves around the graph. And if we start here, the probability of moving moving in that direction, moving to John's turn is 1/2. Probability of Tanya winning is 1/2. And so we can say that the probability that Tanya wins, call it PT, probability that Tanya wins is equal to, well, two cases. The probability she immediately flips ahead and the probability she immediately flips a tail times the probability that it's John's turn and that we eventually get to Tanya winning. But we notice that we have a symmetric diagram, right? The probability of ever getting from T to JW is the same as the probability of ever getting from J to TW.
To TW.
So the probability of ever going from John's turn to Tanya winning is 1 minus the probability that Tanya wins from the very beginning. And so we're using that concept of ever again. Yeah, the red lines are, ever getting there. Probability of 1 minus PT. Because the probability of ever getting here is PT. And it has to be one or the other. So now we can just solve, and in all three of these we wind up with the same probability, 2/3. It's nice to have 3 different methods so that you can check against each method. Probability that Tanya wins is 2/3. Probability that John wins is 1/3. So does that help your sense of thinking of that sort of collection of the infinitude of possibilities?
A little bit. So it's basically lumping them. It's basically using the fact that all probabilities have to add up to 1 and then subtracting an event that probability is known for.
In this case, yes, I guess it does always use that. I hadn't thought of it that way. Yeah, I guess it does always use that fact that, yeah, the probabilities do have to add up to 1. That's, with probability 1, one of the things that are defined happens.
It's probability 0 that the game goes on forever.
That's true. And to make a completely rigorous proof, we'd probably have to say that. Yeah, but that's an easy limit.
Right.
Yeah.
So in this context, states are just kind of like bins.
Yeah. And I'm gonna so the next thing I prepared tonight was a discussion of Catalan numbers. I'm gonna go ahead and begin to transition us into that and point out. Well, I'll go ahead and I'll say what a Catalan number is. In computer science, for anybody who studied computer science, there's something called I guess this is pronounced Dick numbers, and these are the number of ways that we can have well-formed sequences of parentheses, meaning that you always have at least as many open parentheses as closed parentheses, and at the end of a statement, you have the same number of open and closed parentheses. And we can immediately see, the analog of the coin flip problem, trying to, finding the probability we get back to 0. We can say, hey, that's like head, head, tail, tail. Head is an open parentheses, and a tail is a closed one. So, how would we go about, counting these up? Which is what we would want to do, for instance, if we wanted to come up with a series form for this, is count up the number of ways to do it. And I think what we'd actually need, like this would be the 4th Catalan number, and we'd want to subtract off the 3rd one, because you could, or we want to subtract off the third one times the first one, which is really just the third one, because we would want to limit those to those that, you know, had not previously gone back to the origin. Actually, we'd have to limit it to, you know, more than just subtracting C3, but anyhow, I'll get back to that. Right? I can't remember. I'd have to, well, C4 minus C3 times C. Maybe 0 minus C2 times C1. Anyway, I'm going to avoid the need of doing that. Let's just come up with a few Catalan problems. So this is one version of it. We're going to do the mountains of Catalan, which I think is how it got the name Catalan numbers. Let's say that we go up a mountain and then we come back. Well, there's one way to do that. Then we can count the number of mountain ranges that go up twice and down twice overall. I guess there's just 2 of those. And then we can count the number of mountain ranges that go up 3 times and down 3 times. And of course, yeah, this is a very ideal mountain range. We always go up and down by the same increments. And of course, it gets harder and harder to know when to stop. It's part of the fundamental nature of counting problems. That's why so many counting methods begin, do the really simple thing first and then correct for overcounting. But this is tougher, and very often with tougher, we wind up thinking in terms of recursive methods. So in order to get to C4, let's see if we can break this down into cases. Let's see, well, we could build on the mountains that we have in the previous case above. So we could take the C3 mountains and then just add an up and a down right afterward. Okay. So that would be, well, there are going to be some others though. There are going to be some that weren't home after 3 ups and 3 downs. Huh. Well, some of those were home after 2 ups and 2 downs, but not after 3 ups and 3 downs. So C2 and then up. Well, we can't go immediately down or else we'd be part of the C3 crowd. So it would be like that. Okay.
So we're adding the 2 ups and 2 downs at the end of C2, or?
Yes, we're taking the C2s and we're adding 2 ups and 2 downs. It has to be 2 ups and 2 downs. And then we're taking the C1 mountains. Those are a little trickier. We could do 3 ups and 3 downs. We can't go immediately down after that first up or else we'd be part of the C2 crowd. We could go up and then down and then up and then down, down. I think that, and that's all the cases. But, you know, we combine these two. The first one has to be an up and the last one has to be a down, right? What that means is that what we're adding on really starts sort of like a level above. Then we're adding a Catalan range. So overall, it's C1 times C2, whereas the previous one is C2 times C1, and the previous case is C3. Well, I guess we could say times C0 and say that there is one mountain range with no ups and no downs. It's the trivial case. And so in general, well, first we could say C4 is this, and we see 5 times 1 plus 2 times 1 plus 1 times 2. Is there anything else? Now I feel like I haven't done this right because I felt like it was going to, I felt like we were going to get 14 if my memory serves. So what did I do wrong? Oh, right, the mountain rate. No, we can't start with C0.
Does it matter whether the extra little bit is on the left or on the right? Like if it does, then there would be asymmetrical versions for four of the C3s, where you could add the little range on the left, and that would produce a different result than if you had it on the right.
Oh, it's not that. It's that I haven't hit the last case, which is that we take the trivial to C0 and then add something and then add, in other words, we start with nothing, but we have mountain ranges that never come back.
Otherwise.
Yeah. And those wouldn't have been built off of any of the previous cases. There we go. Now that equals 14. So that's good. That's good. Sorry, that's my own brain fart at the end. But this does. Do we see why this comprises all possible cases? It's based on the last time the mountain range touches the ground, going left to right. The last time the range was Catalanian before it became finally Catalanian. Okay, so yeah, that's nice. We have a recursion now that helps us compute further and further Catalan numbers. And if we want, we could write that generally as Cn plus 1 is equal to the summation as k goes from 0 to n of ck times c n minus k, I think.
Mhm.
Yep. Okay, good. So we have a recursion, but not a formula. So, okay. What's another version of this problem? Okay. I like this this alternate version a lot because it doesn't appear to be the same problem at first, but so we're going to count triangulations of convex polygons. In other words, if I have a hexagon, and I want to know in how many ways can I chop this particular hexagon up into triangular pieces. What would that be? And we can call this like the sixth triangulation number. Not triangular, but triangulation number. So how do we come up? Well, let's see. T3 is trivially 1. T4. Well, seems pretty easy. That's 2. T5 is tougher. I'm doing this by cutting off the top as a triangle and then filling out the rest of the quadrilateral below. Or if we don't cut off the top as a triangle, we can draw it to vertex. And chop the rest of that up into a quadrilateral. Or we can draw it to another vertex, but not draw it to the first vertex. We get 5 total. So this starts off like Catalan numbers, except we're a little further along. So we might conjecture. It's a pretty weak conjecture at this point. We have 3 numbers in a sequence, and it's kind of like looking at the Fibonacci numbers and going, I have a sequence that starts 1, 2, 3. Maybe it's Fibonacci. Maybe the next number is 4. Maybe it's 14. Maybe it's 28. What we, maybe a weak conjecture might be, hey, look, it's going to be Catalan numbers, but we'd need to come up with a methodology. And so let's see if we can do that with some sort of general polygon. And we don't have the advantage of like a left to right, like starting like a direction that we could take with Catalan mountains. Of course, something like that is always sort of, it's arbitrary. We do it to break a symmetry. Breaking a symmetry is very often gives us a starting point. One way to break a symmetry is to just choose a perspective to work from.
Mhm.
And that works for us in lots and lots of combinatorics problems. How many interior or facial diagonals are there of a cube? The easiest way may be to say, hey, if I'm at a vertex, 3 of the other 7 vertices are neighbors along an edge. So I can draw a diagonal to 4. 4 times 8, correct for overcounting, divide by 2. Since we count each diagonal twice that way, we get 16 total diagonals. We got 4 interior and 12 on the surface. So picking a vertex to work around is obviously a common technique. And how do we work cases here?
Are you doing T6 or T7?
This, I suppose we could go ahead and jump to 6. I drew 7 up here. Actually, you know what? No, let's do 7, because why not? What we want is a generalized method anyway. And I don't think we really need to know what T6 is to see the building process. But I'm going to say one case is to just chop off the top vertex. Don't draw any diagonals from it. And what do we have in that case?
Triangulate the n minus 1 gone.
Yeah, so T7 is going to be T6 plus some other stuff. Okay. Well, if we do draw diagonals from that red vertex, well, we could start here. I'm going to kind of go counterclockwise here. Well, then we could triangulate the rest of everything else. We've got T6 again. Or we could draw a diagonal there. In which case, the number of ways to triangulate the piece on the right is T5. But now we've also got to triangulate the piece on the left. How many ways can we do that?
Two.
So 2, which is T4.
Mhm.
T4.
But there's a problem with this. What problem could we run into?
That it was previously counted in the second T6 term.
Right. We want our cases to be disjoint. Either that, or we can go back and use like principle of inclusion exclusion. But anytime we're reaching for PIE, we we run the risk of things getting overly complicated. So yeah, we're going to assume then that this vertex itself gets cut off from at least the top one. And so we are only going to have the number of ways to triangulate a triangle, a simple triangle. Okay. So then our case where we draw diagonal here is that we do not draw to either of the vertices. I don't know if we call these 1, 2, 3, 4, 5, 6, 7. We don't draw from 1 to either vertex 3 or 4. That means that we must cut one off from those vertices. And so each time we go through these cases, we're triangulating a polygon on the right and a polygon on the left, but this space in between is what we're cutting off on the left that keeps our cases disjoint. In which case, in fact, I'm going to kind of scratch this out and start over. What we've really got is T7 is T2 times T6, where T2 I'm going to trivially define as 1. Oh, wait a minute. Is that right?
T3 times T5?
We are going to have T3 times T5. Did we have T6 twice? Oh, yeah, actually, we're fine. We do have T6, T2 times T6 twice. I'm gonna, yeah, I'll fix that in a moment. It doesn't really need fixing, but I'm gonna fix it for the sake of writing it in a nice way. And T4 times T4, then T5 times T3. And if we take this stuff and turn it around again, really the very first case that we did where we cut off vertex 1 from everything, we can kind of stick that on the end for the sake of making this into the same recursive summation after we replace the T's with the C's. And we've got the same thing again. Well, that's cool. That's nice. We have 3 problems that are all the same, and they're all related to our original coin flip problem. This dancing around the number line. So now, how is it that we get a formula though? These recursive equations are, they're summations. They're not even just linear recursions, which would lend themselves to formulas. But we have to do something different, and there is one more version of this problem, and this one, or actually there are a bunch of versions of this, but this is the one that gives way. And help me know that I have correctly chopped off an 8x8 square.
Yeah.
I hope this is an 8x8 square. Okay, good. So path walking. If we were to, just walk from the origin to 8, 8, we'll say starting point and finishing point. And maybe we could say, hey, we're only going to take paths that are 1 unit at a time that go north and east only. And an example of that could be that path right there. And if we wanted to know the total number of paths, it would be 16, choose 8. 16 moves, choose 18 of them to be north moves. And it's a pretty standard combinatorics problem. Well, if we wanted to make this look like Catalan mountains, we could make the paths like that. Then, well, we could draw in a diagonal, the main diagonal, and then we could have the moves look like that. And there we have a Catalan range. So, well, how could we describe Catalan ranges in terms of paths? Well, we could say that we never cross the main diagonal. Well, that we start out, we never cross, we're never below the main diagonal. Okay, so that's what we want is C8 will be the number of paths from start to finish, the origin to 8, that never are below the main diagonal. It turns out having a really nice probability analogy at the end, and that I still have never quite found an easy way to explain, and that I hope to one day, or at least an intuitive way to explain. But the number of paths that are never below the main diagonal. So here's what we're going to do. We're going to count some. We're going to walk some of these paths together. Actually, I want us to all pick a different path. But instead of saying that we're never crossing below the main diagonal, I'm going to draw a second diagonal. This is the one we're actually not supposed to touch ever. If we never go below the main diagonal, then we never touch this red diagonal. I'm going to give the red diagonal a name. I'm going to call it the diagonal of doom. So if you touch the diagonal of doom, you're over with, your host. We're not counting you. So here's what I'm going to do though. Yeah, I'm gonna wonder, can we work this as like a complementary counting problem? Can we count the number of paths that do touch the diagonal of doom, subtract those off, and then have the total number of have the 8th Catalan number? So I want everybody to come up with such a path, one that touches the diagonal of doom, and we're going to see if we can come up with a way to count those. But if every one of us does one, we'll be able to have this conversation more easily. So now, here's what I'm going to do. I'm going to alter all of our paths that each of us have made with 8 right moves, or 8 east moves and 8 north moves. Right and up, however you want to do it. I'm going to identify the point at which I hit the diagonal of doom. And I'm going to say that when I hit the diagonal of doom, that like that my soul split. Dun dun dun. This is how doom happens. So my soul split, and my ghost began to take a path that was a mirror image of the rest of my path. So here's what happened to my ghost. It went, instead of going 2 to the right, next it went 2 north, then it went 3 to the right, and then it went 1 up, and then it went 2 to the right, and then 1 up. And so I wound up at 8 8. My ghost wound up at 9 7. Where did your ghost wind up?
-2, -3?
No, you're always going north and east still. You're just switching the north and east once you hit the diagonal of doom. So no
I think I
minuses.
got the 8-8. I chose a very simple path: 5 ups, 8 rights, 3 ups.
So you hit the diagonal of doom at 6-5.
Yes. Yes, 6-5.
Okay. And so then your next 2 up moves, your move should be up, and then your ghost goes 3 to the right from there.
Oh, thank you. I'm sorry. So 7-9.
Right, 9-7.
Well, no, because I did 5 up and then 8 across.
Right out
So
your
so
string.
so at 6, 5, then I'd go up 3.
Okay. Tell me your path again.
All right, the path was 5 ups, 8 rights, 3 ups.
Okay.
Very simple path.
So up, 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 right, 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 up, up, up. So here's what I want you to do. At this point right here.
Right. In the flip.
No. Is that the right one?
It would be
I
6
should
rights.
have
Right?
one
6
more.
rights to hit the doom.
Yeah, I didn't write them all down, did I? There we go.
Right.
Okay. At that point right there, we switch your rights to ups and your ups to rights. Now notice that in total you have 9 rights.
Then I get the 9 rights and 7 ups.
Yeah.
I also ended up at 9-7.
Turns out we all end up at 9-7. If we've gone k plus 1 steps to the right and k steps up when we hit the diagonal of doom, what should remain is 8 minus k minus 1, and then 8 minus k. But we take those and we flip those to 8 minus k and 8 minus k plus 1. We flip the remaining, and then we add those together, and we get 9-7 always. And that's simply because we've always gone exactly 1 more to the right than up when we hit the diagonal of doom, right? So that's to be expected, yeah. We're taking that extra up move that we need to go and turning it into an extra right move. And that's how we end up 1 step to the right of where we should have out of the 16 total steps. Okay, so what does this have to do with anything? Well, now, what I claim is that there is a 1-to-1 correspondence between the paths from 0 to 8-8 that touch the diagonal of doom and the path from 0 to 9-7. Because any path that hits the diagonal of doom, those paths, as we have already shown, have a 1-to-1 correspondence with the paths that go to 9-7. From the point where they hit the diagonal. We can either do 1 more right and get to 9-7, or 1 more up and get to 8-8. And in order to get to 9-7, you cannot get to 9-7 without hitting the diagonal of doom. So hitting 9-7 means that you necessarily hit diagonal doom. So that's how we know for certain we have a 1-to-1 correspondence. And now we know that, and in total, there are 16 choose 9 ways to get to 9-7. So we know that in total, the number of ways to get to 8-8 without going below the main diagonal is this. And in general, we can generalize this. I'll go back to non-graph paper. Formula for Catalan numbers. Cn is 2n choose n minus 2n choose n plus 1. And you know what? This would be fine as far as I'm concerned. This is perfectly fine, but we might be interested to see what happens when we write it out with factorial notation. Not that we need those parentheses. And it does turn out to be kind of interesting when we find a common denominator. We'll multiply the first fraction by n plus 1 over n plus 1, and the second one by n over n. And that'll give us n plus 1 times 2n factorialized over n plus 1 factorial times n factorial minus n times 2n factorial over
That's what it was.
plus 1 factorial times n, and that just equals 2n factorial over n plus 1 factorial n factorial, which if we want to, we could say that's 1 over n plus 1 times 2n choose n. This was, so that's the formula. It's a nice formula. Nice closed form without any, without having to compute multiple combinations. But this is why I was saying there was a nice probabilistic interpretation at the end. If you were to take a path, if Nissa were to take a random walk and be home after 2n steps, the probability that she remained only on the positive part of the number line is 1 over n plus 1. It's probability she never crosses over to the negative side before being home after 2n moves. Now that would include her being home earlier than 2n moves. So, you know, that's why I said that the terms in our infinite series weren't exactly Catalan numbers. We'd have to do some subtracting off of previous stuff and maybe use that recursion to get that exactly right. But there we are. Any questions or thoughts about this? Well, I think this is a good stopping point. Yeah, we'll call this a good stopping point. Well, thanks for coming. Did you enjoy it, Tanya?
Yes, it was fun.
So tell me about your studies in math.
Well, I have a bachelor's in mathematics, but I haven't like.
Did you say you and your